Hello and welcome to our lesson on enlargements. In this lesson, we will build on our prior knowledge of the volumes of 3D shapes and the enlargements of 2D shapes. Here's what we'll cover. We will start by understanding how changing one dimension of a shape affects its surface area. We will then examine how this dimensional change impacts the volume of the shape. Finally, we'll learn how to use ratios to calculate these changes efficiently. In our previous lessons, we've developed a solid understanding of volumes of 3D shapes. We've learned how to calculate volumes of various geometric solids, enlargements of 2D shapes. We've understood how scaling affects dimensions and areas in two-dimensional space. With this strong foundation, we can now delve into how these enlargements affect not just the surface areas, but also the volumes of three-dimensional figures. This skill is particularly useful for solving problems that involve scaling objects up or down in real-world contexts. For instance, if we need to enlarge a swimming pool's dimensions while keeping the proportions similar, knowing how the volume changes will help us calculate the new water capacity efficiently. So if you'll excuse the pun, let's dive in. Let's begin by refreshing our understanding of scaling up one dimension. Suppose we have a line segment of length 1 unit and we enlarge this by a scale factor of 2. The new length is simply 1 times 2 equals 2 units. This is straightforward because it involves only one dimension. When we're working with 2D shapes like squares or rectangles, the concept of enlargement becomes slightly more complex because we have to consider both length and width. Let's use an example to make this clearer. Consider a square with a side length of 1 centimeter. If we enlarge this square by a scale factor of 4, each side will now be 1 times 4 equals 4 centimeters long. Let us compare the areas of the original and enlarged shapes. The original area of the square is 1 times 1 equals 1 square centimeter. The new surface area after enlargement is 4 times 4 equals 16 square centimeters. Notice that while the length is multiplied by 4, the surface area is multiplied by 4 squared, that is 16 instead. This is because in 2D both dimensions, length and width, are scaled up by the factor. This leads us to a general rule. If you enlarge a 2D shape by a scale factor of k, the new surface area will be multiplied by k squared. Now let's extend this logic to 3D shapes like cubes or spheres. Here we must consider length, width, and height. Again, let's develop our understanding with an example. Consider a cube with a side length of 1 centimeter. If we enlarge this cube by a scale factor of 4, each edge will now be 1 times 4 equals 4 centimeters long. Let us now compare the volumes of the original and enlarged shapes. The original volume is 1 times 1 equals 1 cubic centimeter. The new volume after enlargement is 4 times 4 equals 64 cubic centimeters. The volume is multiplied by 4 cubed or 64. Again, it's not just a simple factor, but one that considers all three dimensions. This observation leads to a general rule. If you enlarge a 3D shape by a scale factor of k, the new volume will be multiplied by k cubed. Let's end this lesson by summarizing the relationships we've explored through ratios. If the length is scaled by a to b, then the surface area is scaled by a squared to b squared. Additionally, if the length is scaled by a to b, then the volume is scaled by a cubed to b cubed. For example, a shape scaled by a factor of 2 to 5 would have surface areas in the ratio of 4 to 25 and volumes in the ratio of 8 to 125. In today's lesson, we explored how enlarging one dimension of a shape affects its surface area and volume, reflecting on how the scale factor gets squared and cubed respectively. We then discussed using ratios to efficiently calculate these changes, and we applied our newfound knowledge to multiple examples. Understanding these relationships is crucial for practical applications such as resizing models or determining material quantities in construction. By mastering these concepts, we can confidently tackle problems involving the scaling of objects in both 2 and 3 dimensions.